there's work on those. The main difference between peer-to-peer systems, hybrid peer-to-peer, and cache networks is that in the hybrid peer-to-peer system, the search takes place within some sort of overlay topology, but the download doesn't affect that topology. Whereas in cache networks, when you download the content, it then gets stored at the node's alone download path. So in that sense, the modeling is different. So we'll conclude now with the fourth chapter of breadcrumbs. So you can really think about a cache network as some big cache. Like this is basically a distributed caching system. You can think of it as just a big cache. And then you can ask all sorts of questions about it, such as, what are the hit probabilities of this big cache? What is the miss probabilities? What is the delay? Etc., etc. But there's one major difference between cache networks and just a big cache. And that is the issue that you can send a request into the network looking for content. It might be somewhere in the network, but you may not find it. Right? And the way that we looked at it earlier, where you send a request towards the custodian, and you look along the way, there might be copies of the content just one or two hops to the side of your path, and you'll never see them. Right? So as a result, I forgot to put on, should be a piece of content. So as a result, okay, we need to find better ways of searching for content. So we have to also keep in mind that when I say searching for content, I mean, how do we route misses? Okay, there's a cache miss, we need to route it to some next hop. Where is that next hop going to be? Okay, so content search is basically, how do you route misses? And we want to search, specifically we want to focus on searching where content is likely to be, and we'll know or completely or very negligible state sharing amongst caches. So I don't want caches to notify each other what they currently store and make decisions based on that. So here too, there's been work on content search within like in Nutella, where the basic approach is I think to broadcast or random walk. I forget which one. I noticed in Marbach did work on, which is very similar actually, around the same time, also in 2009, when breadcrumbs were published. They were trying to figure out how to know that things are not in the network, so you don't search for them. And they use a similar scheme as we did, but with important differences. Also, you can improve the system not by searching better, but by storing better. So Ismail Ari, in his papers and in his thesis, talked about sort of how do you, instead of, you route things like you do in a standard network, but you can use machine learning techniques to cache better in each one of the caches. So our work and his work are sort of like, they're orthogonal, maybe could be perhaps combined to make some interesting performance. So breadcrumbs. So I once talk about breadcrumbs and discovered that some people didn't have the cultural background to know what breadcrumbs are. So just briefly, there's a story about Hansel and Gretel who were walking in the forest, and they wanted to find their way back in the forest, so they took a loaf of bread and began to sprinkle little crumbs of bread to keep the path, which of course the path didn't survive for very long, and it didn't really help them. I don't recall in the story that they actually found that trail when they escaped the witch.
It's not very, that doesn't augur well.
Oh, that's a good point.
Yes. I hadn't really thought about it.
That's a good point. Okay. Maybe I should change the name. Okay, so with breadcrumbs, when a content piece gets downloaded from the custodian, every cache that it passes through puts up these breadcrumb pointers, these breadcrumb entries. What they have is, they have basically 5 pieces of information. They have the file ID, just a key to this entry. They store where the file came from, like what was the previous hop, where it's sent to, and the time when the file was last sent, and the time when the file was last requested at this node. And in this talk, even though, so you can first of all see that the vprev and vnext are set up by the original file download, and the timestamps are then updated as time progresses and the events that take place at the cache. Now, in this talk and in most of our work, while we have this information of where the file came from, we don't really make use of it because we have to sort of focus on one specific scheme, and so we assume that we had this just pointing to where the content was sent to. That's where the content was more recently, because where it was sent to was cached later in time. So we're going to look at that pointer, where the content was sent to, as our breadcrumb pointer.
I'm just curious, what kind of data structure would you use? And how many entries would you expect?
Well, in terms of the number of entries, that very much depends on the timeout factor. So we propose not to keep these breadcrumbs forever, but rather to keep them for a certain period of time until they eventually time out. So you can control that parameter because you can decide for how long you want to keep each breadcrumb for until you time it out. So in that sense, we can control the size of the list. In terms of, I would believe that in terms of the benefits you get, I would believe that the time you store things depends on the propagation delays in the system.
I mean, how many pieces of content would you decide to support? Billions?
Yeah. I mean, I would assume.
So,
but I wouldn't have to store
number
for
of
each.
entries be.
But I only need to keep like a track of them over a short period of time after they pass through. In other words, I don't need to keep. I don't know all the file IDs in advance. I just need to, once I see a piece of content, then I give it like sort of like it has a value, and I put it as an entry here. So we also kind of do a data structure. I believe that I would try to do. Well, you're going to be referencing this a lot, but inserting it probably at a lesser rate, is my guess. So I probably look for something that had like a good search, like the search was, let's say, relatively low, maybe like a hash table. That would sort of be my first guess, but I haven't at all thought about this question. So how do we use these breadcrumbs? How do we make use of these pointers? So we start off with the same way we start off every cache network system. So you have a request, and it goes all the way up to the custodian. Once it reaches the custodian sends the content down, and the content gets then stored at each one of the caches along the way. And now we also have these pointers pointing to the next hop, right? We only have them at the caches, not at the custodian, and then pointing along the download path. And now, when a new request comes in, let's just say for a moment that it came in at this node over here, and let's say that the content has been evicted by the caches next to it, but not by all the caches on this path. And then we send a request to the custodian originally, just like before. We check the cache, see if it has the content. If not, does it have a breadcrumb? It does. Well, we can then follow the breadcrumb if it's valid, and until we reach the piece of content. And if it happened that that piece of content too has been evicted, so what we call a dead end. Okay, so there's no content over there. In that case, we say, okay, there's no content. There's no pointer. That was the destination before. So we don't have anywhere to go using the pointer. So now we can simply reroute the requests towards the custodian. We also, well, you might ask, well, then when it reaches this node, isn't it going to just forward the request back down here and you'll remain in this infinite loop? Well, the answer is that one of the ways that we time out these breadcrumbs is we say, well, I'll look at this also in a moment, again, that if you really get a request for content coming from the opposite direction in which the breadcrumb points to, you invalidate the pointer because you say, obviously it's not in the next hop. We show that we actually know more than that in just a moment. So how long do we keep these breadcrumbs? Well, we have these deltas, delta Q, the time after TQ, after the last request, delta F, the time after the last file passed through the network. And so we just use soft state timeout in order to determine when, as long as you're requesting content and you're using this pointer, then you're going to be sending it down and maybe refreshing content downstream. So we can continue using it if the request rate is fast enough. And naturally, if the file passes through here again, then we know that the trail somewhere downstream may be refreshed. So we continue using the pointer. Once we find the content, there's a question: how do we download it? We can either download it using the shortest path, or when we found it at some node, we want to get to a user, so we just use the shortest path within the network. Or we could look at, we can just backtrack along the request route, and that way maybe gain some benefits of other requests that are being forwarded to along the same track, already serve them on the way back. So we looked at both of them, and they gave more or less the same results. Sometimes one was better than the other, depending on all sorts of systems, but overall they were pretty similar. We've shown two or three major interesting analytical properties once you assume that these deltas are identical for all nodes, not for all files, just for all nodes. In other words, for the same file I, you want to have the same delta value for requests and for content at all the nodes. Hey, this would require some amount of coordination. between the caches. And I said before that we want to make this completely without coordination, but this value can remain steady and constant throughout the lifetime of the network. And so it's not like sharing state content where you say at every few seconds you announce what you're currently storing in your cache. So this is only when you join the network you need to know this value, and then you're set. So if that's true, if we have that condition, then not only do we, so let's say we have the scenario I mentioned earlier, where a request for content comes in the opposite direction of where the pointer points. So naturally we can say, well, we're not going to use that pointer now because it's pointless. I could do it, but it's just going to send it back to me, right? I'm going to send it to here. This routing table obviously says send it back here, so it's just going to ping pong back and forth. So naturally it's pointless to do it. But the truth is, it's not just that it's pointless. We actually show that we know by the fact that it forwarded this to here that all the pointers along the way have already been invalidated, that they're no longer active. And what that really means is that the content that was stored at that node, while it might be there now because of some other download, of course, but for the download that generated the stream, that copy is no longer stored there actually. So we can show that. So this means that this node, just by looking at local information, knows something about several hops down what the state is. In a similar way, we also have trail stability. Stability means that if you start going down a path, then it's possible that the path is getting shorter because things are being rolled back, let's say because of those requests we just now saw, where a request comes in the opposite direction. But timeout, meaning that just the soft state timeout, that can't occur in the middle of the trail. The intuition for this is, so what I mean by that is this. If I start sending a request downstream here, then I'm wondering, could it be that somewhere downstream there's one place where the trail breaks? See, this one is no longer active. This one is. Maybe I'm going to miss all the rest of the trail because one of them timed out before I reached it. So I actually have seven more hops to go, but I'm not going to see them because I missed one hop. The answer is if you assume that these are the same and that the download delay is greater than the request delay, at least with a high probability, then with high probability this cannot occur. So that we know if we start down a path, we're going to explore all the path, or whatever's left of it, what's not being rolled back maybe from the end. That means also that basically what that means is that these breadcrumbs can expire before the ones lower down, which makes sense because of their timeout is set basically on when they saw things, and they saw things earlier. So that means that the breadcrumb trail will time out in this direction. And so we get this property with high probability of border node, which basically says that close to the custodian, you're going to have requests with no breadcrumbs, so the requests are going to be forwarded to the custodian. But outside of the certain radius, with high probability, you'll be forwarding requests away from the custodian. So you get some load distribution in the network, and you can control that load distribution to some degree by your timeout period. How long do you keep these breadcrumbs?
Is it possible for an individual node to get two different breadcrumbs for the same file?
No. At least in our system, we assumed one. You could have a system which had multiple pointers and gave us the time for each of them and made decisions based on that. But in our system, whenever content comes in, a breadcrumb doesn't get modified, the direction of a breadcrumb, the pointer, doesn't get modified by a request, only by content. And whenever content passes through the node, it's wherever that content was forwarded to, it points in that direction.
If two requests came to one node, would it always and it's not, the content is not sitting at that node.
Right.
Oh, there's only one place that would look for that, though.
Yes.
So it would route both of them the same direction, and thus it would end up with the same.
Exactly. And in fact, one of the nice things about this thing is that it can help if you have a policy like LRU, which keep things in longer if you request them at higher rates. So one of the motivations here was to say, if we can route as many requests as we can to the same node, right, using these trails, these breadcrumb trails, then for popular pods, that will keep those requests, that content longer in there. It didn't work out as perfectly as we had imagined, but because there's a lot of noise, but that was sort of part of the motivation. In terms of our experiment, so we wanted to compare to two things. First of all was the basic approach, just simply routing content directly to the destination, like we do in regular cache networks. And wanted to compare it to a coordinating scheme, one where there's some coordination between the caches. So what we did here was we said let every cache coordinate its content and route the routing content and replacement with the one hop upstream neighbor for that content. So if I have for a certain piece of content, I know what the upstream is. That's one hop closer to the custodian. And then so cache A is a neighbor of cache B, and cache A forwards misses for file I from A to B. So cache A will determine if to store file I or not, depending on what's in cache B, and will determine if to route requests to cache B, depending on its state, etc. So we allow a radius of 1, basically, of coordination between caches, and compare it to breadcrumbs, which has no explicit coordination. There's no state sharing in breadcrumbs. So we looked at all sorts of performance metrics: custodian load, search hops, download hops. When you search for a while, but you find content somewhere, maybe you searched for 10 hops, but it was actually just 2 hops away. It just took you a while to search. So we looked at these things, and we'll just show you a few examples, but there's many more. Here again, we looked at this in this example of the Torus topology. 500 unique files, divided amongst its custodians, same arrival rates, and here we also added some propagation delay into the system, so that we had some more impact to the decision of the time to live. Okay, so these are the proportions that we used. And if we look at this example, in the x-axis we have just 2 cases, caches size 10 and 20. And we have 4 examples. We have 4 results for each one of these scenarios. We have, the y-axis is the cache network topology. In other words, what fraction of requests is satisfied by a cache router? All the rest arrive at the custodian. Okay? So what is the volume of requests? What fraction of the volume of requests was satisfied by the network, was found by the request in one of the cache routers and not at the custodian? So here we'd like those to be high, at least if our intent is to find things in the network. And we can see that, so here we have the leftmost green bar is the basic approach, the going shortest path to the custodian. White is the coordinated scheme, which we discussed earlier. And then we have 2 cases, one with a DFQ and one with a DFSP, meaning different ways of deciding how to route requests once you've found them. Once you've found them, how do you route? Do you do it shortest path or reverse request path? So we looked at both cases. And as you can see, 2 things. First of all, we see that, perhaps surprisingly, the cache, the breadcrumbs improves upon not only the basic approach, but also the coordinated one. It's not so surprising if you take into account the fact that with the coordinated scheme, there's a radius limit, right? Every cache here is limited. It only shares information with some radius that it has. In this case, 1 hop away radius. But breadcrumbs is not limited in terms of how far it can search. So it can search, indefinitely in principle, all dependent on this timeout, parameter. So that it allows you basically, sort of more ability to take advantage of things in the network. And another thing to note is that this seems to be a recurring theme in my work. As the cache size gets smaller, the performance of breadcrumbs gets better. And that's also, of course, makes sense because the custodian, because of the coordinated scheme, all it does is basically allow caches that are next to each other, behave almost as if they're one joint cache. So if the cache size is small, that impact is also small. But with breadcrumbs, you can search the entire network. So you're not limited in a sense in terms of the amount of space you're searching. Yes.
Just trying to watch the time here.
Right. Okay. I'm just going to finish up. So there's other examples here, and there's another example here where we can get back to it soon. I'll just move on to my conclusion. So, quick overview of what we did here. We talked about ANET, which was an iterative fixed point algorithm for approximate analysis of cache networks. Now we've shown here, in addition to presenting the algorithm, shown that it converges, also for random and FIFO, that we've done a lot of performance evaluation and shown how to do factor analysis for its error. Then we talked about network calculus, which was sort of complementary to the ANET, where you try to bound the flows and not estimate them. And here we've proven theorems about the bounds over LRU, demonstrated performance. Then we talked about ergodicity, which was basically how much does the steady state depend on the initial state, what you can mean. showed examples where it does depend very strongly, and formulated conditions where it does not. And finally, we talked about breadcrumbs, which is an approach for dynamic search for content in cache networks, which relies on implicit coordination between caches. Here we've shown some analytical properties, we've done performance evaluation, and also we didn't mention it here, we also did some causality analysis trying to understand how much of this special search for content impacts performance by intelligent routing of requests versus how much does that intelligent routing generate a more favorable state in the system for a content search. So without just 2 slides about what it is that's sort of still open-ended, in addition to some of the questions that were raised here. So we realized in our ANET work that the misstream, the dependencies there are going to be can have a very large effect on the performance. And so we wanted to, one of the things we've begun doing, and we already have a model built up, though we haven't, it wasn't part of the thesis, is develop a tractical Markov model for modeling these inter-arrival distances in the network, in a misstream. Assuming that the arrival process was IRM, what are going to be the dependencies in the misstream? So we have here, actually, we already have a Markov chain, we have the whole structure, but we haven't had time to explore the values we get and what do they imply. And it also might be able actually to be expanded to non-IRM arrivals, though I'm not sure that that's actually feasible, but it might be possible. And the other topic, which we've sort of done a lot of work on but hasn't reached maturity yet, is that of cache inference, where you look at the misstream of a cache, you try to determine properties of the cache itself. Specifically, we're interested in the eviction rates at the neighbors, because if we could know the eviction rate of the neighbor, we could also maybe make decisions on, is it likely that a piece of content I routed there just a few minutes ago, is it still there? If it evicts things very, very frequently, maybe it's not there anymore. But if it does it on a slow scale, I might be able to find content there. So here too we have a few models that we've sort of developed, some of which I'm more confident in than others. But we also here sort of like would like to sort of maybe complete this, after the thesis, and then that could be also used, let's say, in breadcrumbs or other approaches that do dynamic search. You can use this information, where to search for content. That is it. Pass back. Thank you.
So before we close this to the committee, are there any last questions?
Yes.
In a couple of your slides in the breadcrumbs and before, you basically showed that things get better when the cache size is smaller.
Yes.
But as Mr. Towsley mentioned before, this is also the trivial case where nothing works as it should. So focusing on this trivial case sounds a bit...
Well, first of all, I'm not trying to say that the caches are going to. Let me say 2 things about that. Number one, there is a debate going on now, amongst those that research cache networks, if indeed caching everywhere is a good idea. There is a lot of discussion about that. Is it going to be good performance? The cases that I looked at over here, where you have 500 files and a cache size 10. I mean, I think that I'm being optimistic in terms of the ratio, right? I mean, many more files than there's going to be cache size. I can also assure you that I've run these experiments also with larger caches. I simply showed them over here for these values, but I get similar results. It's only a question of the gradient. In other words, how do the changes in the system affect the performance of the system? With breadcrumbs, that's actually not a case where I'm concerned about that, because with breadcrumbs, when in the modeling cases, I agree with you. That when you look at the cases where things are worse, even though that may be the correct way that things will be, right? There will be more files than there is storage. So, I mean, that definitely reflects what we would expect to occur in an actual system. But with the breadcrumbs specifically, the results there show that you improve performance not because the caches are small, but because you're not limited in how much content, cache space you can search through. So even if you had larger caches and you got good results in terms of the performance, like of other systems of, let's say, of the shortest path or the coordinate schemes, you could still do better with the breadcrumbs. It might cost you a longer search path. That's some of the results we didn't show over here. But you can still do better in that sense. I'm also not claiming that it's better in every way. The one example that I skipped over here, you can see, for example, is where I say, like, if you look at the download distance, okay, how far was the content I found from where I found it, right? From where it was downloaded to, right? So you can see here that I have 3 results. This is the file ID is by order of popularity. Okay, so these are the most popular files, and these are the less popular files. So this value obviously grows. You can see over here that the shortest path you get the largest distances. For coordinated, you get better distances. And in the middle, you have our approach. For this example, for example. So I'm not claiming that it's all is rosy and this is the best way to do everything. I am claiming, though, that the fact that you're not limited in the scope of your search, of sort of how much caching space you can explore, because you can follow these breadcrumb trails, is beneficial and will improve as the network grows, by the way, even if you don't change the cache size. There's another result for that if the network size grows, you can explore more caches, so you'll get more content. And yes, and as the cache size is relatively small compared to the number of files, there's more to explore. Okay?
And if I may, there's another question.
How about, I'm a little bit worried about time. You can have an infinite amount of time with him afterwards. How's that?
Easy for you.
Nobody has infinite amount of time.
Unbounded.
Because I want to make sure that we have enough time to ask questions within the committee also.
Good.
Okay, one second, let me sign off my family here. Okay. Anyway, hope you enjoyed it. 1 second. 1 second, Abba, you have a bit of static there. 1 second. The static will go away in a moment. 1 second.